So I'm going to talk about astrometry and photometry with undersample detectors from space. This is a domain that a lot of people aren't very familiar with. I've spent a lot of years trying to figure out how to do these things well. I'm going to explain to you some of the challenges and the opportunities that come from it. So one of the goals is to convince you that it's possible to do photometry and astrometry, but it's not necessarily easy. It's a new world of analysis that people are going to have to get used to in terms of having to deal with undersampled PSFs. The question is, well, why do we have to deal with undersampling? People on the ground ask these questions all the time. And the reason is that pixels are expensive. Pixels in space are very expensive. And there's a natural trade-off between circuits, downlink, all these things are expensive. So there's a natural trade-off between sampling and real estate. And my wife is an agent, and real estate always wins. Real estate takes priority. So there's a similar trade-off with distortion. I remember when we first started producing HST data, my advisor, Ivan King, was furious that there was always so much distortion in these detectors, but the reason is they want to have as few bounces as possible. So they don't care where the images land on the field, they just care that they're sharp. And so that's similar to a undersampling thing, and distortion is not a major problem. So before HST, people said undersampling just makes astrometry just not doable. And that's not true at all, but I remember being told that when I was in graduate school, that you just can't do astrometry with undersampling. And it's not true, it's just challenging. If you think about it, the ideal PSF for astrometry would be a top hat function that's the size of a pixel. If the top hat is too small, then you move it around and you don't get any slosh from one pixel to another, so you have no clue where it is within that pixel. If you make it a little larger, you get slosh sometimes, but not always. If the size of the PSF is much larger than that, then you can move it around and there's not very much slosh. But if you have a PSF that's exactly 1 pixel in size, you move it around and no matter where you move it, you have the same amount of slosh from 1 pixel to another. And it's that slosh of flux from 1 pixel to another that tells you where the star is. Now, obviously, we're not going to have a top hat PSF, but it's just worth thinking about the fact that if you have a PSF that is about the size of a pixel, you can do great astrometry with that. Okay, so undersampling, a marginally sampled two-dimensional Gaussian would have 13% of its light in the central pixel, if it's centered on a pixel. That doesn't include any light in the halos and such. With WIP-PIC2, about 20% was in the central pixel for the planetary camera, 45% for the wide field camera. That's what I started with. And nobody thinks about WIP-PIC2 anymore, but that's how I started. So ACS gets about 23%, with C3 UVIS gets around 18%. It's the closest to being well sampled of all the HST detectors. With C3 IR can get over 50% of the light in the central pixel. That's very undersampled. So JWST can get anywhere from 60 to 15%. The 200 and 200 microns, it's just barely well sampled. And Roman is going to be about 30% of the light in the central pixel. It's not going to be really bad, but it's also going to be a challenge. So in this talk, I'm going to talk about how to deal with undersampling, benefits of space-based observations, and different ways to approach PSF modeling. The current space-based observations that I can play with are HST and JWST. Euclid is starting to get some good data. The techniques that I've been developing for HST and JWST, I understand they work perfectly for Euclid. I have some collaborators in Italy that have some early data, and they're using essentially the same techniques that I'm developing, that I developed for HST, JWST, and I'm helping get developed for Roman. So it'll be very nice once Euclid takes images of the bulge. We should be able to just pop out good star lists and astrometry and photometry. So then at the end, I'll talk about plans for the Roman pipeline and the program implementation team. So the benefits of space-based observations, of course, are you have no atmosphere. There's no seeing to deal with. You have no daylight cycle, especially at L2. Hubble goes around the Earth, and so that's kind of a daylight cycle. You get high Strel ratios. The optics is quite well known, but people always think it's better known than it really is. You have a long-term stable observing platform, which is all good. So you can do something 10 years later, and essentially the data quality is the same. You don't need to do too many corrections for things. But the challenges are, of course, undersampling. You get sharp PSF features even in the outskirts of the PSF. So because of the optics, you can still get bumps in the PSF in the outskirts that are just as sharp, almost as sharp as the core. So this can be a challenge. With HST, it's called breathing and jitter variations. And you can sort of see on the left here, that's the residual PSF between, say, the average exposure and the exposures in maybe a 20 or 30 image series. And you can sort of see that sometimes you have more flux in the core and sometimes you have less flux in the core. And with HST and the breathing, it's changing the telescope length. And so that really doesn't change the shape of the core very much. It just sloshes some flux from the core to the outskirts. That's a pretty low frequency thing, so it's pretty easy to deal with. Web, you have 18 mirrors, and even though the PSF is as sharp as it's supposed to be, depending on exactly where these mirrors are, you can get slightly different PSF features, and these PSF features can be high frequency. So you end up with, you take a set of observations, you see the exact same residual in all of those observations. And so you have to do different things to account for this. You can't just have a low frequency improvement for the PSF. Hopefully for Roman, I think it'll be a low frequency change in the PSF because it's more like HST, but not at all as extreme. So space-based PSF models, when I started working with WIFPIC2, my advisor, Jive King, had GTO time and wanted to get good results out. But we got residuals that showed clear problems with the point spread function. When in a star, if it's on the left side of the pixel, then you had a bias that pulls it to the left. And if it's on the right side of the pixel, then there was a bias that pulled it to the right. And all of that was telling us that something's wrong with the PSF. So I did a lot of thinking about how can we model the PSF better. And thankfully, I don't know much optics. I think that's actually a benefit sometimes because people that really know optics think that they need to find an optics-based solution for things, and they don't look for empirical solutions sometimes. So it was great that I didn't know optics, so I didn't know what should be there. It's uncharted territory. DFO and these other PSF modeling routines work for the ground with well-sampled PSFs, but they don't work at all for space. So I started thinking, so if you have like two different shapes of the PSF, one sharp with the core and one just a simple Gaussian, they can both describe the pixel distribution that you see there. But the difference is that in center is 7% of the pixel off. But how in the world do you know what the true underlying function is from that if you just see the pixels? And the answer is, it took me a while to realize it, that you don't actually ever need to know what's going on underneath the pixels. You can just look at the pixels and see what the pixels do. So whenever you fit stars with a PSF, you're always dealing with a pixel integrated PSF. And whenever you see the PSF in images, you always have pixels that represent the pixel integrated PSF. So there's no reason to try to figure out what's going on underneath the pixels. I mean, there are some reasons for it, but for the most part, you really just don't need to try to figure things out at that detail. And so my procedure is just to try to do an empirical description of what stars look like at different faces of pixel. And so let's say you have a star here at the center of a 5x5 grid. Usually when I fit stars in Hubble images, I just use 5x5 pixels because almost all the flux is in there. If this is like, with WFirst, you end up with 30% of the light in the central pixel, maybe 8% in the side pixels, 7% above, something like that. That's what you deal with. If the star moves to the boundary, to the left side boundary, then you end up with maybe 20% and 20%, and then a different distribution of fluxes in pixels. If it moves to a corner, then you end up with something different altogether. So the question is, you don't really have stars that land at the centers of pixels. Theoretically, you do, but you never really have a star that's exactly at the center. And even if you did, you wouldn't know the star was at the center of a pixel. So you have to do something about that. And so I started thinking, well, what happens if you have a star there and you just have a pixel in a different location relative to the center of the star, and you move this pixel around? This pixel, as you move it slowly, is going to change the number of electrons in that pixel very slowly. It should be continuous because the PSF is a continuous function. So all you really need to do is map out exactly how much flux this pixel would measure if it's at different locations relative to the star. And so in order to sense that, the PSF, I like to call it psi because it's kind of like a wave function. It tells you what fraction of things land in each pixel. Basically, to figure out what fraction of light lands in the pixel, you just take the pixel value, subtract sky, and then divide by the flux of the star. And that gives you the fraction of light that lands in a pixel that's at a certain offset. So the challenge with measuring the PSF is just mapping this function psi as a function of delta x and delta y. And so you do that when you have lots of stars. Each pixel in each star gives you one sampling of the PSF, tells you what fraction of light landed at that distance from the star center. You put all of this together and you get a lot of samplings, a lot more than this. We often get 10,000 samplings of the PSF, and you need to construct a simple, smoothish model for that. And so basically, if you look at all of the samplings, say at the center of the PSF, you can see a nice smooth curve like that. And that's essentially, you're just looking at the PSF directly. So that's just like what happened if you took that red box and moved it across the middle of the star. You see exactly how much light would land at different offsets. And then you can shift it down by a half a pixel and do the same thing, and it's not as sharp. So basically, I end up doing this for lots of different fiducial grid points, and that allows me to construct a PSF that can be sampled nicely. So basically, for HST, I sample in every quarter of a pixel in X and Y. That gives you 16 samplings per pixel. This has a lot of degrees of freedom. So you need to put in a lot of different normalizations, smoothness constraints. You don't want the PSF varying chaotically from one grid point to another. Normalization, you want to have a total flux of 1 within a certain aperture. Subpixel normalization, I'm not going to go into that, but that can be complicated if pixels are sensitive. Say the center of a pixel is more sensitive than the edge or the corner, then that actually can be treated directly in this effective PSF notation if you know how to constrain it. So there's a lot of stuff that can be done very simply in this formalism. So generally for HST, my PSFs go out to about 10 pixels because you can't really see very much flux from unsaturated stars farther out than that. And unsaturated stars, they're hard to measure, but you want to measure them in a different way than saturated stars. Than saturated stars. And so there are purposes to extending the PSF farther out, but it takes bootstrapping and other kinds of things. For Roman, of course, we're going to want to know the PSF far out, not so that we can do PSF fitting, but just so that we can be aware of the impact of the PSF of these bright stars on the scene. So I'm going to just show you some quick examples of science. I mean, one of the great things about Roman is that we're going to get these movies of sky. And so I've been involved in a couple of projects that give you movies of the sky. And so here is a white dwarf that Peter McGill found was going to have an encounter with a background star. And as it moves back past that background star, it's going to shift the background star, and you can measure the mass of the white dwarf. And it's an isolated helium white dwarf, so you don't get that opportunity to measure such a thing very often. So this is cool. So here's the first exposure we have in 2019. You can sort of see we took another one later in 2019, and that's the target star right there. Another observation a few months later, another one. You can sort of see that the bumps in the PSF are making it difficult to measure the flux and location of the target star. These are things that you have to deal with. And I'm not sure that Roman is going to have to deal with these kinds of things as much, but it's fun to just realize that there's a lot of things you can do with point spread functions. Okay, so you can sort of see that if you look at the star, you subtract the star, you can sort of see that we can do a pretty good job measuring the position of the source star relative to the white dwarf. And then you can measure a mass. So we found the mass to be just a little bit under 0.6 solar masses. Okay, another one that we did recently, Jessica's team made a separate measurement of this, the team that I was on with Kailash Sahu. And there's a source here that seemed to have a very long-term lensing event. But unfortunately, it just happens to be next to a bright neighbor. And the problems that you have with that in space are a lot lower than what you have from the ground, because from the ground, everything is all blurred together. But even in space, it can cause challenges. You can sort of see that the source there is landing sort of just off of various bumps in the PSF. And if the orientation of the telescope isn't perfect, then it can move off of bumps. And so you have to do a very careful job modeling the point spread function of the bright star so you can remove it to figure out where this faint star is. We're going to have to do some of that for Roman. Hopefully, we'll have some automated tools to make these things easier. And hopefully, we'll have situations where you don't have these spoiler stars so close. In fact, we will. We have to, because this is very improbable that the spoiler star was just sitting there. But you can sort of see that the outer parts of the PSF, these are just exposures taken one after another. The flux in the outer parts of the PSF changes with time. Roman, it should not do that as much. Here's a project that I've been working on with Josh Blackman. He has observations in 4 different Meerkat filters. So here's blue, redder, and then red. You can sort of see the PSF change shape. And the idea is that there's the brighter star here was in a lensing event. There's another interloper star that has nothing to do with the event, but you sort of have to be able to remove these things. And so if you subtract just the general PSF, you end up with residuals like that, just a library PSF that you got from a different data set. But if you model the PSF better, you can actually subtract it a lot better. So there are these kinds of things that we can do with PSFs. We'll try to automate a lot of this so that people can do this with Roman, but I'm just setting you guys up that it's not trivial, but a lot of these tools for Roman, hopefully we won't have to reinvent the wheel every time we have a new set of observations. So HST, everything is a special case right now, but with Roman, we can't afford to have everything be a special case. I mean, maybe 60, 70% of the events should be handleable by the same pipeline, but there are going to be events that are not handleable by a simple pipeline. We're going to have superpowers to figure out how to do the subtractions and these other things well. So basically, the pipeline that we're putting together for Roman is building on what we have for HST and JWST. Roman is a lot more stable than either of those. It's going to be at L2, but it's going to have a single mirror. So it might breathe a little bit in terms of changing the focal plane, but I don't think the thermal situation is going to change very much. It has some jitter, but that's a lot easier to model than thermal variations. And so obviously advantages over the ground, when you look at lensing events, you have 100 times more pixels per star. And so it's much easier to tell the difference between stars that are close. And when you can do that during the event itself, you have a huge advantage because you can just sort of see the light in the event. You're not worrying very much about nearby stars contaminating that. So you can actually measure the color of both stars just from the light curve, because really you don't have a lot of competing light in there. And you know that at the time of the event, they're right on top of each other. So any other things that aren't involved, you can just identify them as interloper stars. Even if they're within a pixel, you can do an easy job identifying them and subtracting them much better than when the lensing pair sort of separate, and you have to measure something like that. So one of the challenges with Roman is that it's got a very, very wideband filter. And the stars are going to have different PSFs depending on how red they are or how blue they are. So this is basically the wideband filter is made up of 5 different filters. I mean, you can sort of just think of it as 5 different filters. So if you look at the bluest filter, we have FO87. That's what a star would look like in that one. The next one, the next one, the next one, the next one. And pretty much every star is going to be some combination of these different PSFs, depending on how blue it is or how red it is. And that's something that we're going to have to deal with. I don't think it's going to be crazy hard to deal with it, but we're going to need to sort of figure out how to put all the data that we have together to do that. So let's see. So the goal of the MSOS pipeline, which the PIT is working on with people at IPAC, is to just do the best job we can with a single reduction procedure. And then we're going to feed results from that to people that need to do more intense science, or just analyze the events that have been analyzed adequately with the pipeline. So the pipeline currently has 4 different prongs right now. One is creating stacks, and create a stack weekly and then seasonally. The stars are going to move a bit during the season, so it's not trivial to construct a good seasonal stack, because stars are going to move by maybe 0.05 of a pixel, which isn't huge, but that's going to end up blurring some things. There's going to be a construction of the catalog is another thing that has to be. So I'll be talking about these 4 things: creating difference images to analyze events and to maybe even find events, and also getting a starting PSF from other observations. The observations of the bulge are going to be too dense to extract a good PSF because they're just way too many interfering stars. So you need a more sparse field so that you can extract a good PSF. And if you want to measure the PSF really far out, you need an even sparser field. But Roman is going to be taking lots of data with lots of different field densities, so it shouldn't be that hard for us to come up with these things. So as far as the stacked reference frame, it turns out it's very similar to constructing a PSF. You just want to know, if I have a pixel that lands at this location in the scene, how much flux is it going to collect? And you can sort of move your putative pixels all around and sort of map out exactly what the scene looks like. So here's a stack of the scene. Here's a close-up of the stack. Here are all the different samplings that would land in that green box. And then you can sort of look at the set of samplings that goes through the center of that star there. And just like the PSF, you have that nice trend showing you what a putative pixel would look like if you move it across the scene. And that allows you to model it with PSFs, with other kinds of things. But the goal is to create a nice stacked image so that people can analyze these images with tools that they already have. Now, this, even though it comes from undersampled data, this is a well-sampled stack. So you can use DAO and other kinds of things to create catalogs and things from it. So that's a very useful thing. So here's what the stack looks like. If you plot it into well, if you look at the first exposure, that's what the first exposure looks like. And you can sort of see, typical star has 2 pixels that are affected. That tells you it's a very undersampled detector. So if you blot the stack that I created into this first exposure, you can't really tell a difference at all. That means the stack has done a good job representing what the pixels in the images show. And so if you subtract the blotted scene from it, you see that around the bright stars, there's some small numerical artifacts. It's hard to get this perfect because you don't really have infinite information. Even if you have 800 images, you still don't have perfect information. And the brightest stars are not the ones that you really care to do difference analysis with anyway. So, but this is a very nice difference image that can be analyzed the way that you all, that can be analyzed like a difference image, even though this image is one-to-one sampled. So it's just regular things sampled just like the image itself. So it's undersampled. And if you want to analyze stars, you need to use an undersampled PSF to analyze this difference image. So jitter is also something that is going to come into Roman. If you have the scene, the default scene started with a PSF that was 10 milliarc seconds jitter in each direction. If you increase the jitter along one of those axes by 20%, then you can't really tell the difference just by looking at it. But if you look at the difference images now, you see something like that. And that's because the stars are actually a little broader than they were in the stack that we made. And so you can actually just do a simple model of that, then correct the individual exposures for this change of jitter so that I'm calling it regularizing these exposures so that you can make a single stack of the exposures that are nice and regular. This technique has been working nicely. Of course, we don't know exactly what the jitter is going to be, but this should do a great job allowing us to construct a single stack. So the catalog construction, I won't go into too much detail on that. Here's a catalog that I made with a lot of artificial stars. And if you just do some finding things with DAO find or something like that, you can do a pretty good job subtracting things. There are some artifacts in some stars that aren't found. For instance, you have a bright star here, you're not going to find a lot of faint stars right in the vicinity of bright stars. So these are the kinds of things that we're going to be dealing with. And sometimes when you have binary stars, you end up with a third star that's there that you can work on ways of removing this. We haven't been pushing this very hard because we're just trying to sort of move everything together at the same time, but there's a lot of improvements that we'll be able to do once we have real data. And when we get real data, we're going to be changing how we do things. So let's see. Yeah. Okay, I'm almost done here. So the difference images, you can sort of imagine the difference images are not like the stacks. So like with the ground, you have a difference image that sort of is in the frame of the stacks that you make. But here, the difference images are just in the unresampled pixels. So there's distortion in these difference images and all these different things. But if you have a distortion correction, you can know exactly where a star should be in this frame, and you can do PSF analysis on it with very high precision. You can say whether or not the change in this difference images reflects a point source or whether it's not a point source. You can do a lot of different things with it. You can test for the PSF shape, throw out a lot of false positives that way. You can find events that aren't in the catalog, look for solar system objects that are moving fast. You can confirm the location. You can say, yes, in fact, this change in the difference image is a fact of the exact position that I expect it to be based on the stars that I know. And you can also look at the significance. This is interesting. I think people want to do this. You can sort of window, even though you can't make a super sampled stack with just 5 or 10 images because the sampling, you need to deal with it. But with the difference images, you can say, okay, let's look at 5 images in a row and see how significant the difference event at this location is. And you can add them all together. And if it's a 1 sigma event in each of 5 images, then it's a 5 sigma event if you add those all together. And since there's going to be dithering, all of that should be extremely straightforward. So we're hoping to be able to put together tools for that, assuming that the difference images get made public. So this is going to be fun and exciting, I think. And analyzing things for moving stars, there are other algorithms that can be done for that. The last thing I'll talk about is getting a starting PSF. Roman is going to be using the LMC field for commissioning. So we'll get a lot of observations of this field. So I just decided to look at what a simulated observation of this field would look like to see whether or not it's easy to extract the PSF. And in fact, I was able to extract a PSF all the way out to 30 pixels that was good at the center and good in the outskirts. So it's so here's the original image, and here are the PSF stars that I used. And if you subtract them, does a pretty good job subtracting them out. So it's not going to be very hard at all to get a good starting PSF to start with the Roman analysis. I think that's it. So everything is in progress. The pipeline is getting put together. They have some reviews coming up soon, but this is also a moving target. So we also need to sort of get a sense of what the data are going to allow us to do. Thanks.
I was just wondering, thank you so much. I just want a question related to the intrapixel sensitivity.
Yes.
So are you factoring that in or you covering that?
I haven't started modeling it, but I've done some simulations to figure out how to model it. It shouldn't be very hard at all. Each pixel could be different from each other pixel. Or you could also just have it, the average pixel is more sensitive at the center or the edges. So each of those things we can deal with separately. Because the nice thing about our field, we're going to have a lot of dithers. And you're going to have a star that's relatively bright that lands at every single location and every single pixel. And so that makes it very easy to back out the particular sensitivity distribution within each individual pixel. So I think there's a lot of things that can be done only with this program. And I think the weak lensing people are going to be very excited to see what we can help them with.
And just following up on that, presumably that's a stable thing, the sensitivity map?
I believe so, yeah. I mean, you don't measure it once it's up in space, but they've measured it a few times on the ground. But they have some measurements for it on the ground. So the first thing you want to do is just see whether or not the measurements you have for it help you with reductions.
So from yesterday's talk, we know that Roman's detector quite different some other changes.
Well, WFC3IR is actually a CMOS detector as well, so that's different. I think you're right that there will be some challenges with the brighter, fatter effect that come in. And when you fit up the ramp slopes for things, if the scene itself is changing as flux is collected, that can complicate the analysis quite a bit. And so what does the slope really mean if it's not linear? And these are the kinds of things that we've been talking about, trying to understand what kind of reduction might allow us to deal with that. And we don't want to have to deal with, all the up the ramp frames. That would be a lot of work. But something like that might be necessary, but I hope not. At some level, it's just a perturbation on the PSF, but it's not even a single perturbation because it changes as flux is brought in.
Jay, is the pipeline and the simulations progress far enough that there's a place we can go to get astrometric precisions and photometric precisions?
Not quite yet, not quite yet. They have some reviews that they want to do first before they start putting things out there. But I believe the software will be public. Is that right, Etienne? At the end? Yeah.